Hi, I'm Rhett Jesse, and today we're going to talk about the Metrix digital proximity system, specifically how to use it with an unknown shaft material. We're going to use the Metrix shaft calibrator touch select, which is a way that we can get a calibration on an unknown target material. So we're going to use this shaft that will simulate a shaft in a rotating machine or a reciprocating machine like a piston rod, and we'll take readings on it and look at our results, and we'll also look at how you'd use this in practice. So we'll be going from the classroom situation that we have here to what we see in the field, and so we'll be discussing both those scenarios. To begin, what we use is we use this cradle, and it's beveled on the bottom so that it can easily go on a curved surface. And then we use this stretchable strap to go around it to secure it to the shaft that we're looking at or to the piston rod, and we'll see how that goes. So we'll go ahead and put it on, and it nicely centers and aligns itself, and then you grab the strap, you bring that around, and then you just firmly lift up on it and make sure it's nice and tight. And that's how it fixes itself to the shaft. Then we use the static calibrator that comes with it. And this static calibrator will go on top of this fixture here. Well, to do that, the shaft calibrator can be used by itself as a static calibrator, and I'll show you what I mean by that. It has, right now it has a 4140 shaft target material on it. I can change that out to any target material. But in this case, I'm not going to use the bottom portion. I'm just going to use the adapter that's on the shaft because we're talking about an unknown shaft target material. So with that, what we'll do is we'll go ahead and put this on the top, and we'll screw it down and make sure it's nice and tight. Okay, it's firmly on there. And what we want to do is the top actually swivels, and you feel there's like this little clicking motion. And this clicking motion, every click is 10 mils of movement in the axial direction. So as I turn it, it clicks 10 mils. Turn it again, another 10 mils, and so on and so forth. So I can get a full linear range, 0 to 90 or maybe 0 to 180, depending on what type of probe I have in. Today I'm going to be using a Metrix 2030 8mm probe, so we're going to be looking at distances from 10 to 90 mils. Okay, we also have a metric version of this. Instead of in 10 mil increments, it goes in 200 micron increments. So that's the difference. So 200 microns for the metric version, 210 mils for the English version. So that's what we have. Okay, so what I'm going to do is I'll put it down to the what would be considered the first marker, and that we'll call that 0 right there. We'll call that 0. Then I'm going to insert my probe into the device, and I'm going to put it down until it contacts the shaft, and I can see that it's contacting the shaft right now. And then I'll go ahead and tighten this up. So right now I'm in contact with the shaft material. And now every time I move it counterclockwise, I'll be changing the axial distance by 10 mils for this particular calibrator. So we'll go ahead and go to the 10 mil position. That's the first one. Okay, we're going to connect the digital proximity system to the computer so we can take data. So we have the probe set in the static calibrator for the shaft, or the shaft static calibrator. This is the touch select version because there's no numbers coming out of here. It's by feel. You can do that. And it makes sense when you're on site, when it's dark and you can't see and it's difficult to get light in, you can still feel for exactly where the indents are as you adjust the static micrometer. All right, so let's go ahead and plug in the digital proximity system to the computer. And to do that, I take the digital proximity system, I remove the DIN rail cover or mounting. This is a special plate we have on so I can access this USB port. So I'll go ahead and connect to that USB port, and that basically connects the computer to the software. And I can hear my connection. I'll go ahead and start the software now, and it should come up with an MX2030 9-meter system, and that's what I'm expecting. All right, so what we have here is we have an MX2034 transmitter. It's for position, MX2030, 4140 material. That's what it's set right now. It's really unknown, but I set it at 4140 because I don't know any better. And we'll look at the results and then make some decisions from there. This is also an 8mm probe for a 9-meter system, and we're going to be looking from 10 to 90 mils. So that's our setup. So what we want to do next is we'll do a verification. We're going to go in and basically see what we've got here at 10 mils, and we've already positioned the probe to be 10 mils away from the target material, or the shaft material in this case. So now we'll say get. Okay, we have the warning screen that says make sure you're in position before you take data, which I will, so I don't need to see this anymore. We'll let that fill in, and then we'll adjust it in 10 mil increments until we have all the data. And you'll feel this as you go. You just gently turn it, and then it will click in. So that is really the secret sauce when it comes to using this device. What you want to do is you want to, after it takes data, before you go to the next one, just move it gently to the next one, and then you'll feel it click. And when it clicks, you know that you're in the right position. And we'll take data, and since we don't know this material, it's not 4140 steel, I can tell you that right now. Now, really, I do know the material, but for the purposes of this video, we're simulating we don't. All right. So we're using 4140, and you can see it's not linear. We have 260 millivolts per mil. That's way off from our standard. It's supposed to be between 190 and 210, and it's not. So we'll continue to take data. Again. And we do this until we get to 100 mils. And then we'll just look at our results. You can see the scale factor is way off. We're probably going to saturate by the time we get to the end because it's non-linear. All right, we've taken the data, and what you can see is that it's not linear at all. And because we don't know what this material is, I didn't have it set up right. So what we want to do is let's just go ahead and do a custom calibration to see if we can bring this into specification. And this is the power of the digital proximity system, is even though it's unknown, I can still get linear results. And we'll go ahead and do a custom calibration right now. So we'll hit perform a custom calibration, and then we'll take data again and see if we do any better. We'll have to go ahead and let the tables populate. What's nice about this is after we have this done, and we can export this file and we can use it on other DPS units. So it makes the configuration of those units with the unknown target material easier. So that's a nice feature of the digital proximity system. All right, so now we're going to go ahead and do that verification again. I'm going to go ahead and move the probe back to 10 mils, so I'll go ahead and do that. Okay, I'm going to make sure that my probe's on the bottom. It is. All right, now I'm going to move it to the 10 mil setting. There we go. And we're going to go ahead and we'll take data again. All right, so we've been successful in being able to take a nonlinear system with an unknown target material, get the values into the digital proximity system, then we do a custom calibration, and we can see now that the data is very linear. It's between 190 and 210, with the average scale factor being 201 millivolts per mil. Well, that's outstanding results. On site, we do the same thing that we did in the classroom. We'll remove the shaft calibrator touch select from its case. We'll go ahead and assemble it just like we did, where we took the shaft calibration micrometer and put it onto the shaft calibration cradle or mounting fixture. so that way we can fix it to the shaft. As the technician puts those items together, he'll then move into position so he can comfortably place the shaft calibrator touch select onto the shaft, and he tightens up the strap so that it's secure. Then we insert the probe, we tighten down the adjustment knob so that way it stays in the right position, and then we move the shaft calibrator touch select to its first 10 mil point. And then we move it in 10 mil increments until we have the data. After 100 mils, we'll look at the data and we'll determine, do we need to perform a custom calibration? And we will perform the verification over again. So we're going to go ahead and do that. So we performed a custom calibration. Now we're going to move the shaft calibrator touch select back to 10 mils, and then we'll retake the data back to 100. So we'll do 10, 20, all the way back to 100. And now we'll go back to the classroom. Thank you very much.